Hi everyone. Wanted to talk about Coulomb's law, which is the kind of stage zero for our understanding of the electric field, and basically it's right here. And the interesting thing about Coulomb's law of the electromagnetic interaction is that it looked exactly like Newton's law of gravity. And so just in the same way, you've got the force of gravity is basically proportional to both of the masses divided by the square of the distance between them. The static electric force is also proportional to the distances between the charges and the magnitude of those charges. Now, what's new that we're adding is this idea of the electric charge. And basically, every object has got some amount of charge, and that charge represents how much the object really feels the electric forces around it. In the same way that the mass of an object, the more massive an object is, the more gravitational force it produces. In the same way, the more charge an object has, the more electric force or the influence it exudes and experiences. The SI unit for electric charge is the Coulomb, and Coulomb is a very large amount of charge. Typically, in laboratory environments, we're talking about microcoulombs. That's a more normal size. A lightning bolt is on the order of 25-ish coulombs. So, if you're talking about a full coulomb, you're really talking about a small lightning bolt. So, there's that. So the other thing to recognize about the electric force is that it is a force and therefore is a vector. And so if we have multiple sources, those multiple sources are going to produce multiple forces, and therefore we need to add them like vectors. And so there's going to be a lot of vector math in this first few chapters. And so if you need to brush up on that, go ahead and do that. But basically there's nothing new. It's just going to be utilizing the tools we've used in the past in order to do that. And so when you imagine the electric force, I want you to kind of think about a picture like this. And this is the electric field that I was talking about before. And so if you notice here, this Coulomb's law, basically what Faraday did, and I'm simplifying of course, is he said, you know what, Coulomb's law has got two pieces. There's a piece that's associated with the source, and that's what I've got as capital Q up here, right? And then there's the thing that experiences the electric force, the receiver of the influence, and that's a little q, sometimes called a test charge. And so what's interesting about this is we can split this into the components that involve little q, which is the test charge, and then everything else. So if I imagine just this piece of the formula, that's what we're going to call the electric field. And basically, we take Coulomb's law, split it into two pieces, and define the electric field as the remaining piece. Now, right now, we're just playing with the math. But when we get to the more complicated phenomena and the interaction between electricity and magnetism, this concept becomes impossible to get along without. So that's why we're introducing it now kind of at the simplest possible stage. So this is the picture you should have in your mind of what the electric field looks like. You have in the center a charge, an electric charge, and surrounding it you have all these arrows, right? And so basically if I were to take a test charge and stick it anywhere, that arrow represents the force that that charge is going to experience through this formula, right? So the closer we get to the charge, the larger the arrow, because the force is larger, right? The force is always pointing away from the charge, and we presume this is a positive charge. Now the one thing that's different about the electric force from gravity is that there's both a positive and a negative. So the nice thing about Coulomb's law here is that it actually accounts for that. So if we have two positive charges, that's a repulsive force. They don't like each other. Negative charges don't like each other, but plus and minuses, they do. So in electricity, opposites attract, and the same type of charge repels. So that's the thing to remember, is opposites attract. And so that's why here we've got basically all the arrows point away from the positive charge. So if I were to put another positive charge, it would fly away, right? If I put a negative charge, the electric field stays the same, but the negative sign here flips the sign of the force and actually creates an attractive force through that combination. So the field stays what it is, but I can either get a force of attraction or a force of repulsion, depending on whether the test charge is positive or negative.